Okay, so Unit 5, Lesson 5, we're going to solve polynomial equations using what we just talked about in Lesson 4. So solving polynomial equations, the main method we're going to use to solve these equations is factoring. So there's two things you need to know in order to factor these. First thing is, you need to know how to factor out a GCF. So in example 1, the greatest common factor of these three terms is 2x. So if I factor out 2x, this is my factored polynomial. Okay. Once I factor that polynomial, I get a quadratic that has three terms. And this is where we factor using our method from Lesson 4, where we have to find numbers that multiply to be 9 and add to be -6. So if I think about it for a second, those numbers are both -3. So my factored form here is x minus 3 and x minus 3 equal to 0. If I want to clean this up a little bit, this becomes 2x times x minus 3 squared equals 0. So the whole reason we factor to solve is to get factors which are easier to solve for, because I just need to find out what makes the factor of, and I'll do these separately, what makes the factor of 2x equal to 0, what makes the factor of x minus 3 equal to 0. So one of my solutions is, in fact, 0, because 2 times 0 is 0. My other solution is 3, because 3 minus 3 is 3. So the way I represent my solutions, I would say x equals 0 and x equals 3. And if we notice, if we look at our polynomial, this factor, x minus 3, is being squared. Okay, it's being squared. So we consider 3 what's called a repeated solution. And we talk about how repeated solutions connect to graphs a little later on in this lesson. So if we move down a little bit, in this box I kind of explain that factor appears more than once. So we call that a repeated solution of 3. And that connection is made when we graph it. So if I graph this polynomial is going to, I'm going to draw it in this little space over here. This polynomial is going to have x-intercepts, okay? X-intercepts at 0 and at 3. And if we look at it, it is a polynomial that is cubic. Its highest degree is 3. It's to the third power. So what that means for the end behavior, which we talked about earlier in this unit, the end behavior goes up to the right, down to the left. So this is the thing the connection I want us to make. The graph touches the x-axis but does not cross at 3, and it crosses at 0. So when we talk about repeated solutions, if we have a factor raised to an odd power, it crosses through the x-axis at that solution, or at that 0. If it's raised to an even power, the graph touches, I'm going to use another phrase for that, I say it kind of bounces off the x-axis. So I'm going to kind of explain that more in depth in example 2, where we find zeros, which is essentially the same as finding solutions as we did up top. So finding the zeros of a function, the way we do that is we take the function, -2x to the 4th, plus 16x squared minus 32. We set that equal to 0. Okay? We find zeros by setting our function equal to 0. And then we factor this function, or we factor this expression. So again, we look for a GCF. In this function, I could factor out 2 from each term. The next level thing is to notice the first term is negative. So what I would do is I would factor out -2. So I'll be left with x to the 4th. And this would be minus 8x squared plus 16. And that is equal to 0. So factoring this is very similar to factoring our example 1. I know it's x to the 4th instead of x squared, but these can be factored the same way by finding numbers that multiply to be 16 and add to be -8. So both of those numbers are -4. And the way I represent my solutions, represent my factors, since this was x to the 4th, my factors are x squared minus 4 and x squared minus 4. And I'm going to set that equal to 0. So to write this a little bit cleaner, it would be x squared minus 4 squared equals 0. So like I said before, we are trying to find what makes this factor 0. So I'm actually finding what makes x squared minus 4 equal to 0. So I set my factor equal to 0. So this becomes x squared equals 4. If I square root both sides, x equals 2 and -2. So my solutions are 2 and -2, and they are both repeated, okay? And the reason they are repeated is because of this factor being squared, okay? This factor being squared means that they are repeated. So the big picture here, you're going to have to draw your own graph. But the big picture is I'm going to graph both of my zeros. And let's just say that's -2. This is +2. I'm going to graph both my zeros. And what it is it's noticing that first term tells us the end behavior. So that first term is negative and has an even power. So the end behavior, it's going to be going down to the left, down to the right. That connects to our end behavior from lesson 1 in this unit. So to draw that end behavior, I'm going to do that first always when I graph. That would be my end behavior. And we just got to remember, since both of our zeros are repeated, it's going to look a little funky, but they both bounce. So when I go from -2, it's going to bounce off, it's going to rebound, and it's going to bounce off at +2. Now, this little dip I showed in the middle, I don't really care if it's very accurate. I care more that you know the end behavior and that it bounces off at these zeros, okay? If you are ever doing this, what I expect you to do is show the work, but you can always, always, always use Desmos to check your work. If all you did was look on Desmos and copy it down on a quiz, I wouldn't give you the full credit. You'd still earn maybe a passing grade, but it wouldn't be, if you're thinking about a 3 or a 4, it wouldn't quite rise to that level of understanding that is required by a 3 or a 4 score. So just keep that in mind. The factoring is essential to understanding, if it bounces or not, and kind of what the end behavior is. So moving ahead, I am going to explain this, and I'm going to try and explain it the best I can, where you are understanding what I expect. So how we use this thing called the rational root theorem is the rational root theorem basically gives us an idea of how to find the possible rational zeros of a function, okay, or all the real solutions of an equation. Now, we are going to use this for an example or two, but I'm going to show you what I expect of you, okay? So for this rational root theorem, you take the factors of the last term, the constant term, and you divide them by the factors of the leading coefficient. So in example 3, the way I would represent this rational root theorem is the factors of 20 divided by the factors of 1. So it's essentially going to be positive or negative 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, and positive or negative 20 over 1. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible rational roots, okay? Now, what I want us to understand is one big thing here, and this we cover in the next lesson, but for this polynomial has a degree of 3. So what that means is it has 3 solutions to it, or this equation has 3 solutions. So out of these 12 possible solutions, there are 3 actual solutions. So the way we test if something is a solution or not is we use synthetic division, which again, it's connecting to something we learned before in this unit. So I'm going to quick just test. I'm going to test the solution of positive 1 in my polynomial. 1, negative 8, 11, and 20. Okay? If this is a solution, I'm going to end with a remainder of 0. So let's try it. 1, 1, negative 7, 4, 4, 24. Well, we just found out that positive 1 is not a solution. So we would just naturally move to negative 1. See if that is a solution. So drop down 1. This is negative 1, negative 9, 9, 20, and negative 20, which gives me 0. So that's good, all right? So we know for a fact that negative 1 is a solution. So I could keep going with this synthetic division, and I could keep breaking this polynomial down and seeing if each of these numbers is a solution. I could be potentially doing this 10 more times to find all my solutions. So what I'd like you to recognize next is that let's see if this is a polynomial that we can factor. And it's remembering that we started with a degree of 3, so this polynomial has a degree of 2. So yes, I can factor this. Numbers that multiply to be 20, add to be negative 9. Those numbers are negative 5, negative 4. So my other 2 solutions are positive 5 and positive 4. And that is nice to know, because then I don't have to do a lot more synthetic division. So basically, you're hunting for solutions, and then you're using synthetic division to test those solutions that you're hunting for. Again, Desmos is helpful when checking answers, but I expect work when I see this on quizzes and tests and things like that. Okay. Moving ahead. Example 4 will be the last example I cover in this lesson. Example 5 I will not cover because that is something I will save. It's more of an extension. So I'm just going to focus in on example 4. And in example 4, the list of solutions is very, very long because what it is, it's the list of factors of 12 over factors of 10. So there are fractions, there are so many different numbers. So what I would like you guys to be able to do is this. I would like you to be able to graph this, and I'll make this show up. But what we're going to do is we are going to graph this polynomial, okay? And it's going to take me a bit because I'm doing this by kind of hand here. So minus 11x to the third minus 42x squared plus 7x plus 12, okay? So this is the thing I would like you guys to know how to do when the solutions are a little bit harder to find. Now, I don't want this to be something that bails you out of having to do work, but I want us to make this connection that the zeros to this function are the x-intercepts of this function. So we'll talk more about solutions in depth in our next lesson, but basically what I'm looking at is this has a degree of 4, so this has 4 solutions. And that's how I find those 4 solutions, is I graph and I check the x-intercepts. Okay, there are different methods. There are different types of solutions that we will talk about in the next lesson. But right now, I want you to know how to factor. I want you to know how to use Desmos to help you find solutions to these polynomial equations, or to find zeros. So just remember, zeros and solutions are the same thing. They tell you the same thing, just in a different format.